Hello everyone, my name is Sagar Gia and I am doing this video presentation for my machine learning project which is on Prudential Dataset from Kaggle. So here is the link to the dataset, so let's go there. Okay, so this is my dataset, Prudential Life Insurance Assessment, and throughout the project I am following the crisp DM process, right from business understanding, then data understanding, data preparation, data modeling, evaluation, interpretation, and then finally deployment. So first comes the business understanding. Why are we doing this project, or why are we building machine learning models on Prudential Dataset? So as you know, people in US get turned off while applying for insurance because the entire process takes around 30 days to assess the risk of an applicant. So Prudential aims to build an automated machine learning models that could take a person's application and directly classify that application into a particular risk category, right from 1 to 8. So our target variable is an ordinal variable going from 1 to 8. So let's start our project. First of all, we load in the CSV file. I have named it train, and as you can see here, it has around 60,000 cases with 128 feature variables. So I'll be applying principal component analysis to reduce my features, to reduce multicollinearity, but that will come ahead. First of all, I'll have to deal with outliers, NAs, normalization, and all the other things for the data pre-processing. There's a lot of data pre-processing in this project, so please bear with me. Now let's check the structure of the dataset so that we can figure out our pre-processing task. Okay, so as you can see in the dataset, there are a few continuous variables and everything else is categorical. There are lots of NAs in the dataset. So first of all, let's deal with the NAs. Okay, so this is to check the total number of NAs in the dataset, which is quite a lot. So now let's check the number of NAs by each column, so that which column has how many NAs. So here you can see that there are a few columns which is lots of NAs, even more than 50% of the data in the column is NA. So we'll directly remove these columns because they'll hamper our analysis. So all these columns will be removed from the dataset, and the rest everything seems okay. There's this one column that has 19 NAs, so we'll try to do some data imputation for this NA and remove rest of the columns. We can afford to remove these columns since we have so many columns or so many features in our dataset. Okay, so these are the column numbers that I've noted. So removing these columns from the data. Okay, here we get our train underscore new one. Okay, so now let's again check the structure of the data, or the structure of the variable which had 19 missing values. Yeah, here it is. So we know that it's now a continuous variable, and it doesn't make sense to build a machine learning model for data imputation since there are so many features and it won't make sense, and we are only dealing with 19 missing values. So what I'm doing here is using the mean imputation strategy, so calculating the mean of the column and imputing for all the missing values. So let's do that. Okay, and now just to be sure, let's check the number of missing values again in the dataset, and yeah, now it's 0. So we are going good. We have removed all the missing values and done data imputation for them. Okay, I forgot to show you the dataset, so let's just check the dataset once just to get a brief idea. So first is the ID column, which we will be removing soon, and these are the other columns in the dataset. As you can see, it's quite a long dataset and lots of categorical variables. And final column is our response column, which is risk levels from 1 to 8, which is an ordinal variable, meaning that 8 is the category that has maximum risk, and 1 is the category that has the minimum risk. Okay, so let's go back to our code. Now removing the ID column, which won't make any sense in our modeling, that's why. Okay, now once again checking the structure of the data. Sorry for having so many codes for the structure of the data, but this is just to explain why I'm doing the next step. Now our next step is to dummy code the variables. So there are a few continuous variables which are already normalized. So we do not need to do any normalization for this data set. But all these dummy variables, they are in the int, and we want to dummy code these variables. So for dummy coding, I will use the dummy.data.frame function. So for that function, we need all of this to be in the vector type. So we'll convert all of these columns into type vector so that we can dummy code them. And lastly, this remaining columns, right from medical keyword word, they have already been dummy coded, which is given in the data or in the description in Kaggle. This is already dummy coded, so we do not need to do that again. Okay, so these are the columns that I noted that need to be converted into type vector. So let's do that. And once again checking the structure of the data just to be sure. Yeah, see, now they have all been coded into vector. Now we see that there are some vectors that have 579 levels, 19 levels, 34 levels. Now if we try to dummy code all these columns, it comes around 864 variables, which I tried, and that would be too much even for the principal component analysis. So I'm removing these columns that have too many vector levels. Okay, so there you go, we get a new data frame, train_new3. Okay, so now dummy coding the data frame using dummy.data.frame. Okay, so once this is done, yep, you can see that there are around 205 variables after dummy encoding, and it's not possible to fit a machine learning model in so many features. So I'll be using principal component analysis to reduce the features and maintaining the maximum variance in the dataset. Now the next step is outlier detection. So I'm taking values that are greater than 3 standard deviations from the mean, and I'm only doing this for the columns that have continuous variables, because it won't make sense to do outlier detection in just categorical variables for 0 and 1. Now as you can see, there are a few columns that have lots of outliers. So one possible thing we can do to reduce that is normalizing the data. But since our data is already normalized, we have already kind of dealt with reducing the effect of these outliers. One more reason for having these outliers is that our target variable is an ordinal variable which is having risk from categories 1 to 8. Since the risk is increasing from 1 to 8, the columns will have data that will give more values, have more values or the more count when the risk category is number 8. So that's why these outliers are there, but they make sense in our dataset because of our target variable. And since the data is also already normalized, we would ignore these outliers and move ahead with our analysis. Okay, so now the next step is principal component analysis. And also please note that I haven't made any exploratory plots till now, because since there are 205 variables, it won't make sense to just keep on exploring those variables. So I'll make exploratory plots to show you when I do principal component analysis, and I'll have plots to show you the variance that is being retained. Okay, so now splitting the data into train and test into 70-30 ratio. It might take a while, and yeah, there you go. Okay, so now just checking the table for the response or the target variable. for both the train and the test data. This is just to ensure that our split is going good and there are enough cases for each category, which seems okay. So now we'll move ahead with our analysis of PCA, taking all the columns except the target variable for our principal component analysis. And PRComp is the function in R that does the PCA. Okay, yep, done. Now let's check the attributes that are there for our principal components. So these are the 5 attributes that we have for our PCA. Now let's check the center attribute. Okay, so this is the attribute that has the center for the principal component analysis components. Now this is the rotation attribute, which is basically the loadings of the PCA, or the vector showing the direction of the PCA. So these are a few of the attributes that I'm showcasing for my PCA. For a few variables that R shows, it's showing for 4 variables. Okay, now this is just to check that the dimensions of PCA are similar as our data set, and that's correct. We have 204 columns. Now let's do some exploration, creating a biplot which gives us a brief idea for the principal component analysis, or which components are more important and in which direction they are going, while capturing the variance. Okay, so this is the biplot that we are getting. We can see that these components have more value: medical history 262, 263, and then there are all the other 206 features which we are not able to see because there are 206 features. Okay, so now let's do our variance thing to capture as much variance as we can, or as much information as we can from our data set. So taking the standard deviation attribute, squaring it to get the variance. And now for each attribute we are checking that the variance is how much percent of the total variance in the entire data set. So from this you can interpret that the first component has around covers 19.33% variance of the data set. The second component covers 7.5%, the third component covers 6.25%, and so on. So to visualize this, we'll have to plot this data. So let's make a scree plot for our principal component analysis. Yeah, so see, this is our scree plot, and it shows that around 50 principal components, most of the variance of the data is covered, and the next 150 or so components are only having a little bit of information from our data. So ideally we should pick the first 50 components for our analysis. This is another cumulative plot. These are a few of the exploratory plots just to give a better idea. So see, at 50, around 98% of the data is being covered, and another 150 components are just covering the remaining 2% of the information. So finally I have decided to pick the first 50 principal components for my final analysis. So creating a data frame for our principal components, extracting the first 50 components, and then merging the data frame with our target variable. Okay, and now making predictions on the test data set for the PCA, and then again merging with the response variable to get the complete data frame. Okay,